This is part 2 in a series of videos I'm doing on my visit to NIAR, which is a research facility in Wichita, Kansas. Don't worry, if you haven't seen the other videos, you don't have to watch these in any particular order. I'll put links at the end so that you can go check out the others when you're done. Today we're going to be talking about robots, and to understand some of the problems that they're trying to solve, we need to know a little bit about robot anatomy as well as how we teach robots to do their job. Now, this robot behind me is Jarvis. This is a robot that I custom built here in my shop, designed all the parts, made all the parts myself, and there's a whole series of videos where you can see that. So if you want a real deep dive into the actual making of a robot, that's what this whole project was for. This other robot is an older commercial robot, Motoman HP5. I'm going to be using these two robots to demonstrate some of the concepts for you, and I will intersperse some footage from my visit to NIAR. So if you think about a robot arm as being sort of like a human arm, you've got a shoulder way down here. This would be the elbow, this would be the wrist. This faceplate is where you would give the robot the capability to function like a hand. Typically we call that the end effector. Very often it's a gripper, like I've got some small ones. So here's a little baby gripper here. This one works by pneumatics. There are electrical ones, they're all different types. And here's a much larger gripper. And this is one that's meant to be customized. You would make your own custom fingers, if you will, and attach them with these screws, and then you can squeeze things. Now, in order to move your robot, you're gonna need to send commands to all the joints to tell the robot how to move. But basically, the computer will command each of the joints to position the arm wherever you want. And then you need to send additional commands to control the end effector. And the end effector doesn't have to be a gripper. It can be a plasma cutter, it can be a welding torch, it can be a drill. You can turn your robot into a CNC machine. Whatever you want the robot to do, you would need to attach the tool to allow the robot to do the job. Now here's where things get interesting. If you want a robot to complete a task, you have to tell it literally everything. A basic robot doesn't have any sense of its environment. It just follows commands. And humans don't work like this. Humans have an unbelievably complicated feedback system, completely unaware. The human brain is literally making thousands of tiny adjustments and calculations to how tightly to grip the load, how to orient the load, how much force to apply in order to handle the object properly. It's why nobody's concerned about a bodybuilder picking up his own kid, because grown men are fully capable of determining how to handle the load, how to orient it properly, and handle a baby, even without any prior training. Robots don't have that. They just go wherever you tell them to go. They don't care if anything is in the way. They are unbelievably powerful. And this is why they're almost always behind a fence, because when you tell it to go somewhere, it doesn't care if a human is standing there or not. It is going to complete that mission until it reaches the position it's supposed to be in. And whether it had to knock over a human to get there doesn't matter. So we have safety as one concern, which we'll come back to later. But then we also have to, how do you tell a robot that it's picking up a rock or picking up a baby or picking up an egg? Each one of those situations need to be handled differently. And so you need different kinds of tools on the end, but even just having the right tool is not quite enough. Even if I have this end effector attached to the end of the robot and I go over and tell it to pick up an egg, how does it know how much to squeeze the egg in order to lift it properly? Not all eggs are the same size. If we think of the difference between picking up a rock, picking up a baby, and picking up an egg, you can start to think about some of the problems that engineers need to solve. You do not want robots picking up babies, right? Because there's way too many variables. They are fragile, they are squishy, they wiggle around, and they need to be held in a certain orientation. They don't all weigh the same. This is a very complicated situation for a robot. So don't use robots to pick up babies. But this is not the end of the story. Certainly we can add things to the robot to allow it to sense its environment. We can have force sensors in the gripper so that it knows how much it's squeezing, and we can set limits so that it doesn't squeeze beyond a certain point. We can add springs or any elastic components that allow it to give and be compliant if it needs to be compliant. We can add LiDAR so that it can map out the room and know a little bit more about where obstacles are, even if it doesn't know what the obstacle is. Or we can add a camera so that it can use software to track objects if they're moving, or detect what an object is, or even detect the orientation of an object so that we can know what way to pick it up. All of these things add a huge amount of complexity and cost. They also give you more places for things to fail. Maybe it looks at a block and accidentally thinks it's a banana, or a sensor fails and it doesn't detect something that it should detect, and so on. So as you add more components, you are also adding complexity and cost. Ideally, the simpler the task for the robot, the better. Although we can do much more advanced things with robots. So we need to figure out as much as we can in advance about the various conditions the robot will be operating in, and then we program all that into the robot at the beginning so that it can do its job over and over again. Generally speaking, the less variation there is, the better for robots, that is. Now, once you've mastered one robot and you've taught it how to do its individual job, now you need to teach that same robot how to cooperate with the robots around it. I mean, they need to be able to hand things to each other. They need to be able to wait for each other until the following robot finishes its task so that it can take on the next task, and so on. This thing scales into a really interesting snowball of complicated tasks that need to be done. Now that you've got that really basic introduction to robotics, we're gonna head into this lab where they prototype all sorts of industrial applications with 6 robots all collaborating together.
This is the Robotics and Automation Lab here at WSU and NIAR. We roughly have around 15 full-time staff members and close to 35 to 40 students that work for us. And actually most of our workload is done by the students, and it's kind of overseen by engineers. I'm actually a business management degree myself, so I do a little bit more on the business side, but I help a lot of the engineers kind of understand the business processes that go through the whole process of integrating a robotic cell into an industry. Go ahead, if you want to click that button right behind you, actually I'll get it real quick. And so this is what we call MRAM. It is our multi-robotic advanced manufacturing cell here at NIAR. A little bit of a mouthful, that's why we call it MRAM. But one of the things we do in this cell is a lot of prototyping and a lot of research and development purposes. This isn't something you would see at a customer site. They don't really need 6 robots on 3 different tracks that all share information with each other. But for us, it's really neat. So we're able to test a lot of different inner workings and be able to determine how things work together. We've actually been able to move panes of glass with these robots. Glass is very rigid. Any kind of different tension on different angles generally creates cracks, stresses, and things like that. These robots do it pretty smoothly without any issues, so it's kind of neat. This demo here actually would normally put a suction cup on this MDF board, and then we would, in a sense, run wire harness through it. Over here, we've even attached a large 3D print head, so we are able to do, in a sense, bigger print volumes than what a regular 3D printer would do.
Yeah, that is giant, man.
Yeah, it's very large. Not something we use, so it's not something we use very often, but it is one of those things that we like to highlight, the capabilities. Generally, if there is a product on the shelf, say like drill, 3D printer, anything like that, what we do a lot of is we buy that product, we kind of study it in some way, we disassemble it, and then we try to attach it to a robot. We've done everything from drilling to robotic inspection to pick and place. Some of the more recent ones that we've been doing are pick and place, but with some kind of more difficult materials to pick up, like bags of protein.
Okay.
Or we've actually picked up radiators more recently too. That's a little bit difficult because you can't really bend the radiator fins. So trying to pick them up in a specific way is kind of fun, challenging little engineering process for us. It was funny because we had just the radiators lined all the way across here, just big stacks of them. But yeah, we did this in this cell initially.
Okay, I want to talk about this radiator problem for just a minute because I love solving problems, and so when I hear a hard problem, I get really excited. Now, of course, we don't know all the conditions, and if we could figure this out in a few minutes, we wouldn't be doing this in a research lab, right? So we need to pick our radiator up. There's a couple things. First, we want to make sure it's positioned in such a way that the robot can grab it the same way every time. Also, we can't just use a regular gripper because if you squeeze it too hard, you're definitely gonna bend those fins. They're so fragile, so easy to damage. But certainly we don't want this to happen before it comes out of the box, right? We want the customer to receive a radiator in pristine condition. So how do we get that? If you don't squeeze it hard enough, it's gonna slide out of your gripper. You can't use vacuum or suction because the fins allow air to get in and you're never gonna be able to pull a vacuum. And that's why research facilities like this exist, because they can see what happens if you add a feedback loop, something that's measuring how much force is being applied. Maybe you can get it dialed in just right to lift it perfectly every time. Maybe you need an entirely custom-made gripper that works well in all the different scenarios, or you need a combination of the two where you've got feedback and a custom gripper. Solving these kinds of problems is huge for mass production, right? If you want a robot to be able to work 24 hours a day and pick it up consistently, correctly, without damaging your product over and over again, you need to solve these kinds of problems. And that's what I love about what they're doing here.
Generally what happens is we will purchase all the parts for the customer. We'll get everything in, the robots, if we need fencing, which is generally, especially in industry, industrial robots generally need to be safer, so fenced in is one of the big things. For us in the prototyping kind of world, we use LiDAR scanners and these 6 sensors. So as I get closer, I'll eventually stop the robot. Yeah. So much easier for us to enter and exit the cell without having, fences, lockout, tag out. That's a little
I'd like to talk a little bit more about your proximity sensors and safety devices. Is this a sufficient option for going industrial without caging? Like, can you talk a little bit more about how this system worked, what its limitations are, things like that?
Yeah. So I would not say that this in itself is sufficient enough, especially in a production environment. Okay. If you're doing research and development, you're getting to where it could be more sufficient. We like to use these along with actually using something called light gates.
Okay, I didn't see the light gate there. Okay,
so
good.
Actually, that one's turned off because we have this one on and we kind of enter and exit the cell. We like to really highlight how this works.
And where's the other end of that? Because there should be a, okay, I see it over there.
It's on the fence right there. But that actually helps us use a faux wall. So we use those a lot, but one of those things that it doesn't really tell you is if there's something that's already in the cell when the cell starts. But like lockout, tag out, we've done in the past.
A light gate is very much like those sensors that most people disable in their garage. When you walk into your garage, you break the beam and the garage door stops, except this is a whole column, so you can't just step over it. Anybody passing through this light gate will trigger the system, which should make all of the robots stop moving as you come into the cell. But as he mentioned, once you're on the other side of the light gate, the beams are continuous again. So then you would go to a more robust system like lockout, tag out, which is what he was describing. And all that means is the physical switch that allows the machine to be turned on is in the off position and locked in the off position. So there'll be a tag here that says, don't turn this machine back on, and it'll be physically locked. The person who's working inside the cell will have to come out, and then they're the ones who are supposed to remove the lock. That's the way it should happen, thus making the system much safer for humans to work around.
We work with a lot of industrial robots. Some of the other types of robots are this mirror over here, the autonomous mobile robot. We use these a lot for, kind of ever-changing environments. Generally, they're a little bit different than what you would see at your regular Amazon packing facility, where they follow tape on the floor, reflectors on the ceiling, or anything of that to that nature. These use the same LiDAR sensors that are actually in these 6 sensors here to map their environment and then path based on that mapping. Generally at manufacturing plants or something like that, they have like a walkway for people and potentially a walkway for robots, if they have mobile robots. These don't necessarily need that. They're able to move around that map they've created and path through different objects. If you have people that are bringing pallets of parts in, they're able to actually move around that and not be held up by anything. So pretty neat situation there. So one of the big things is safety, especially in robotics. These industrial robots are meant to do a job and be very repeatable and not be stopped even if you enter or exit the cell. They're going to go right through you. Luckily, that has never happened here. We were very safe. But one of the things is that customers will come to us and be like, hey, this is something that we need an operator in that cell to work on. Generally, we will advise them not to use an industrial robot if that is the case, because safety. So what robots we then advise to use is collaborative robots. A lot of the collaborative robots actually have force sensors built into all their joints. So if they swing around real quickly and they bump into you, it may hurt, but it's not going to go right through you like an industrial robot will. It'll actually stop based on that force sensor. You're then able to start it up later. One thing we do like to highlight though is if you have big giant scissors on the end of the robot, even if it's a collaborative robot, it's still not safe. And funnily enough, we've actually had big giant scissors on the end of the robot for ribbon cutting ceremonies. It's funny kind of how much we use different sorts of tools on the end of robots. But
now I know what some of you are thinking. Why not just make all the robots collaborative, right? If you can add force sensors or add other things that will make the robot safer, you can make them all safer and then you don't need to cage the robot. But the problem is the very thing that makes the robot safer is what makes it less efficient as a robot. Generally, what we want from a robot is we want it to be very powerful and very fast. If you want to move 1,000 parts an hour, you can make a robot move 1,000 parts an hour, but that robot moves so fast. If you have a human in the way, it cannot stop in time to prevent injuring the human. And if you want a robot strong enough to lift a car over and over again, any force sensors or any compliance that you add to that robot have to be robust enough to not be triggered by the car itself, which means that a human, when it gets in the way of that robot, is never going to trigger that sensor. And so there's always a trade-off. You have to give up something. Generally, you are giving up both speed and power or lifting capacity when you switch to a collaborative robot, among other things. But that's why you might go industrial versus collaborative. And that's how we come back to what he said in the interview, which is if they really want to have a human working next to this robot, then we're going to have to switch over collaborative. But what he didn't say is when you switch to collaborative, you are usually significantly lowering the capacity of the robot to go fast, as well as how much load the robot can handle. Now, at this stage of the interview, we found out we were actually supposed to be meeting with the SAE team at this time. We got our times mixed up. So we left this room and came back and continued to interview with another person. So we're going to pick up with Matt Tomlin as we talk more about this robotic cell.
So my name is Matt Tomlin. I am the director of ARC, which stands for Automation Research Center here at NIAR. And what this lab is, really the best way I like to think about it is as industrial R&D. Meaning I can take anything from that reverse engineering side, like all the way up from a napkin sketch, up to a production level machine that operates at 3 shifts a day, almost lights out. Yeah. It's actually the cell behind me called MRAM, Multi-Robotic Advanced Manufacturing Cell, is designed to be able to take any tool that I would like to see on a robot or see in an automated cell, and I can put it on any of these robots behind me and be able to simulate an environment as close as possible to what one of their full cells would look like.
At this point, we started reviewing some of the same stuff you've already heard, but eventually I followed up with the question, why do you need 6 robots? It seems like overkill. Give me an example of a project you're prototyping where you needed 6 robots to test your idea.
Right now we have a wire harness project that we're exploring for an industry. To try to take these manual boards that they lay up on and create all these harnesses so they can go directly onto whatever machine it is. Okay. Right now they do it on tables, they do it on maybe like 45-degree stands or sometimes boards that sit about at 90 degrees. Yep. Here for me, I mounted it on a robot, on 2 robots that are hanging off the rail on the top, right? Yeah. It's so overkill. But what it allows me to do is I can rapidly build that in-house in terms of like a day. I can stick it on the robot and then I can tell you what it's going to lay up like at a 90 degree, at a 45 degree, at a 0 degree. So you can see all sorts of different variations. But having on those 2 robots allows me to be super flexible with it. And especially when I build a tool that does the wire laying, I can see how it operates at different reachabilities for the robot to see if we have accuracy issues. But areas or examples like that are the reason that we use the more complex cell, even though it might be a little bit overkill.
Now, I thought this was really interesting because normally in a production environment, you wouldn't use 6 robots because you could just build fixtures for the things that aren't moving around and the robot can just interact with the fixture. That would be significantly more cost efficient and again, reduce the number of parts that are wearing out, so on and so on. But in their case, they're rapidly changing the scenarios all the time. And so they're using Delmia to quickly program the robots to get whatever the temporary fixture is into the right spot, and then they can interact with that. And if they don't like the position, they can quickly change the position of the fixture from 90 degrees to 45 to flat, as the example that he gave. That's phenomenal, I agree. It's overkill in a production environment, but it makes perfect sense in an environment where you want to rapidly test out multiple ideas. You can set it up very quickly, as he described, within a day in Delmia, and then you come over to your robotic cell and actually do it for real with real robots. Now you've confirmed your results from Delmia in the real world, and then you can go about building fixtures to do this type of setup in a production environment. When you say wire laying, we're talking about you might have a panel that's got, I don't know, 50 or 100 or 300 wires on it, and then the robot will pull the wire out. Is it, like, what happens? Is it also stripping the wires as well? Or like
yeah. Actually, so let's take a look at the tool right back here. So this is one of our very quick prototype tools, right? At the very initial stage, to even test the concept. Is the concept even going to work? So we built this literally in the matter of a couple of weeks. Had the idea, designed it all in 3D, in a 3D environment, so specifically for us, 3DE. When it came down to it, we designed all the different pieces here. So like the spool would be one of them. Yeah. So I'd have a spool of wire. And the way this works is on the inside of the spool, I have this little, almost like a holder, if you will. Yeah. And the way this is designed is so that I can take a piece of machinery, which is just over here, that actually cuts, strips, and labels all of my wire. I can shove it directly into the spool, but as it's pushed in, it holds it while it's in the spool, but as soon as it needs to come out, the tension's built just right to where it just pulls straight out of the spool and goes directly onto the board, allowing the robot to come back over, shove the wire in, and then start spinning this to spool up whatever it needs to spool.
So that part is fully automated then?
It is fully automated, which again is the concept that they were really going for here. But now, I mean, as we look at getting production level ready machines, The big part of this is I can only do one wire at a time. And when I'm talking wire harness boards, I mean, I'm talking a lot per hour, per day. I mean, they need numbers at the end of the day. And so what can I do to speed this up? It's actually where we're looking at, like, AFP machines are a great example. So that's automated fiber placement machines. They have a lot of technology out there that takes tows of these composite fibers. And by tows, I mean just like simple spools. There's 8 spools on one head usually, or maybe you can get up to 16. And they all flow through the center and actually come out to where they are laying up and making a tool. That's actually how a lot of aircraft are made now. Wow, but can I take that same idea now and can I introduce it for our wire harness tool? To where now I feed in 8 different wire harness, or 8 different wires, or maybe 16 different wires, have it all feed through the end of the tool and then lay it directly up onto the machine or onto the board. That's where we're talking numbers and sheer speed coming out of the cell to where I'm producing maybe a full harness in an hour.
And that's what I love about engineering, is because you can, you're constantly thinking about new ways to solve a problem. And when we first walked over here, in my mind, I was thinking, all right, so you have the quick change tool on the top, and this could be set up for one wire, and then you'd have another one, and then another one. But if you could spool all the wires in advance together and then take the whole thing and put it in, that's unbelievable.
And that's what's nice too about working with so many different industries, is we use some aerospace and defense tech to be able to actually translate that concept out to other industries like automotive, for example. And so we get to bring a whole new light and whole new eyes to industries that haven't seen it before.
Yeah, that's fantastic.
So yeah, absolutely everything we do goes through a couple different design phases. So I have my concept design, I have my detailed design, and I have my final design phase. And that's all before I ever even build a full cell. But what I can do, and what we do here in the lab, is design all this stuff inside 3DE, whether or not it's part design, assembly design, whatever it might be. I go through all my kinematic simulations just on a base level, like if my spool needs to rotate here, something needs to open and close, great. But then I can take those kinematic models and I can translate them straight onto the robot using Delmi. And that's a lot of what you see up here on the screen, is we've developed these individual tools. And so yes, you can see it picking and placing. Yes, you see some dry racks, you might see some other bits of automation, but the robot's also sitting there driving absolutely everything. So as I pick up and drop, I can see what that looks like. I can see how much time it takes. And so then I can actually start to produce some metrics. And so we get into those design phases. I don't necessarily just have a design, but I have full-on metrics that have been simulated that I'm shooting for when I build the overall cell. It's also a great tool for doing our internal designs. So I guess our internal studies that maybe the customer might not care about, like reachability, for instance. When I set a robot on a stand, is it gonna be able to reach everything that I need to? I mean, the customer just cares that the job gets done and that it does what it needs to do, right? But when we're designing, reachability is a huge deal for us, because as I put on each individual tool, that reachability is going to drastically change. And so being able to automatically simulate it for various different tools and see different scenarios is always a huge benefit in our specific design process that we go through.
Reachability is one of those things that's really easy to understand, but very easy to underestimate. Essentially, it's, can the robot get the tool into the right position and the right orientation? Now, every robot comes with a working envelope. It's usually a diagram that shows you all the areas that the robot can reach. But when you put a tool on the end of the robot, that can significantly change the reachability of the robot. In fact, even when you put a tool on a human hand, it can change the reachability of the human, right? If I've got a tiny wrench, I might be able to reach into a tiny little space and be able to work the tool around. But if I need a bigger wrench, then my reachability is going to be significantly different. Not just that I can get the tool into the right orientation, this is already going to require me to be able to move my arm a much bigger range, but also clearance. When I go to pull this tool out, can I pull this tool out without hitting anything? Can you get the robot into all the orientations where it can do the job completely? That is, get it in the position and out of position so that it can do the job and not destroy anything else in the environment. So let me give you a quick example. Here we've got just a screw mounted on the end of the robot. Let's pretend that this is a drilling operation, and then assume after that we suddenly need a longer drill, and you can see the difference. All right, that's pretty close for demonstration purposes. So let's just assume that we've got everything lined up. Let's say we need to drill a bigger hole, and all of a sudden I need a much bigger tool. Well, the problem is now the robot needs to be much further away, right? And there you go. I'm hitting one of the hard limits on one of my axes. It's probably this one. Yes. So that one is not going to rotate down anymore in this position. All right, you can be quiet now. Even from my example before, it looks like the robot should have been able to reach that position, but it was just barely out of position enough that I couldn't quite get there. And that's super easy to resolve. It just means the stand needs to be a tiny bit higher, or this needs to be a little bit closer. If all of this was up just another inch or so, the robot could point a little more down. Like, there's all kinds of little tiny changes that would get everything back into scope again. But I would only call those tiny changes if we're in the digital environment. After you have welded and machined and made all of your parts and got cranes and moved all your stuff into place, you are talking about so many hours of labor invested only to find that you're off by that much. And I really just wanted to emphasize how advantageous it is to be able to simulate those situations in advance when the cost is very small, compared to building it by trial and error just to see that you're just a tiny bit off. It was around this part of the interview that we had a bit of a camera malfunction. So just before the camera came back on, we were discussing robotic paint applications. And he was telling us about some of the challenges with robots doing paint in aircraft.
But paint deposition was massive for them because it's aerospace. And so that means if I just get a little bit of too much of an overlap, like instead of a 1/4 inch overlap, I have a 1/2 inch overlap, that whole part can't go on the aircraft because it doesn't meet the certification process. And because it's been painted and it's spent the time drying, that's a huge cost to me. If I have to redo that part, if I have to throw it away or scrap it, whatever has to happen. And so when we build an automated cell, making sure that I don't have errors like that up front before we build it is a huge deal to the project. And especially having time that goes along with it, so I can tell you how many parts I'm gonna produce, at what interval I'm gonna produce them, and at what quality I'm gonna produce them, is a huge benefit.
And you're keeping them from scrapping a part that has a very expensive type of coating on it.
Correct.
Okay.
Where do you see robotics in terms of aircraft?
The hard part with robotics in aerospace is the accuracy. Robots are very, very, very repeatable, meaning when I hit a point, my accuracy is bad, meaning I might be 10 thousandths off, but my repeatability is great, meaning I'm gonna be 10 thousandths off every single time. But that's what's great about some of the tech that we're introducing, like these scanners and these trackers that we use here. If I can get them integrated with robots, which we actually do in some of our projects, but if we can find a way to package that and standardize that, if I have a tracker or if I have something watching the robot auto-correcting for it, that's a big deal. But I mean, that's short term. So that issue is probably gonna be solved in the next 3 to 5 years. Where we're going long term is we wanna get much more intelligent. The problem is right now in aerospace is I can't manufacture anything from a digital environment because every single aircraft out there has a lot of manually drilled holes and a lot of manually done operations. So let's say even if I go service an aircraft, the engineering drawings that I'm referencing are not going to match what I'm physically seeing because it's been so highly manually modified. But if I can manufacture directly from the digital environment, so I know that everything I model, everything I make, and everything I manufacture perfectly matches that digital or matches that engineering model, that is huge for every single industry. And honestly, I think that's the long-term goal of really any bit of automation and any bit of robotics that you see is headed there.
How does someone even come to you with a project?
Yeah, so NIAR is on pretty much every social media platform. You can always reach out. It's always routed back to the right lab here. A lot of our projects actually come from word of mouth. What we do is, I mean, when we make these projects where I make these production level ready machines, people start taking tours of other places, other facilities. They see our cell sitting there.
Yeah.
They see some of the benefits that it can get and like, hey, this cell's working great. And they start looking around for the logo and they ask around and next thing you know, they make it back here.
Well, thank you. Yeah, that's what I wanted. Yeah, man.
Thank you, sir.
Now, of course, robotics is a huge topic, and so this video was not meant to be exhaustive, but I hope you learned a little bit about some of the challenges in robotics, and I hope also that I've inspired you to be a little bit more curious about whether you want to work with one of these guys here. As I mentioned earlier, there's a whole series about this robot build, and I'm contemplating building like an online course for robotics. So if you've got questions about robots or you're interested in that, leave me a comment down below. If enough of you comment, that might nudge me a little bit. As I mentioned before, this is a series, so right up here is gonna be a link to the next video in the series, or I guess to the playlist now. We've got at least one more video coming up. I may add some more later, but thanks for watching.